We've examined several useful Taylor series before. We're now going to look at one more, the binomial series, that can be useful for calculating nth roots for a variety of numbers. Before we can come up with a formula for this binomial series, we need to be introduced to something called the binomial coefficient. This notation we see here, the parentheses with p over k, we read that as p choose k, and it's going to equal p times p minus 1 times p minus 2, all the way down to p minus k plus 1, all divided by k factorial. Let's try out this coefficient for a few examples. Let's start with an example that involves integers. So let's look at 6 choose 3. We know that our denominator is going to be 3 factorial. Our numerator is going to be 6 times numbers smaller than 6, all the way down to the last number, which is 6 minus 3 plus 1, which is 4. So our numerator is just 6 times 5 times 4. So when we solve that out, we get 6 times 5 times 4 over 3 times 2, which is 20. Let's try it now for an example where p is not an integer, because this, we're going to see, is going to be the more interesting case for us when we're establishing binomial series. So let's look at 1/2 choose 6. We know that our denominator is going to be 6 factorial. We also know that our numerator, we're going to start with 1/2, and then we're going to keep taking off 1 from that until we get down to the last value. But the last value is p minus k plus 1, which in this case is 1/2 minus 6 plus 1. Well, that's 1/2 minus 12 halves plus 2 halves, which gives us negative 9 halves. So what we're going to do now is we started with 1/2. We're going to subtract 1 from that. That gives us negative 1/2. We're going to subtract 1 again. That gives us negative 3 halves. Do it one more time. We get negative 5 halves. We can keep going because we have not hit negative 9 halves yet. Then we do negative 7 halves. And then lastly, we do negative 9 halves. Now we can multiply that all together. So on the top, we have 1, 2, 3, 4, 5 negative signs. So that's going to make a negative number. And we have 3 times 5 times 7 times 9. And then our numerator, we have 6 2s. So that's 2 to the 6th. And then we have 6 times 5 times 4 times 3 times 2 times 1 for the 6 factorial. And you can do that on a calculator if you feel like it. I'm going to do a little bit of simplification in order to be able to do that, hopefully without a calculator. So I can, let's see, I can cancel the 5s and the 3s. I can also take a 3 out of the 6, leave that as a 2, and take that out of there. So we can see then we end up with, what's that, negative 21 on the top. And on the bottom, I have 2 to the 6th, and then I have another 2, and then I have a 2 squared, because that's 4, and then I have another 2, so I get negative 21 over 2 to the 6th, 7, 8, 9, 2 to the 10th, which is negative 21 over 1024. So our purpose here is to try to find a series expansion for things of the form of 1 plus x raised to the p. Now, if p is an integer, then 1 plus x to the p is already a polynomial. We can get it just by multiplying 1 plus x to by itself p times. It's when p is not an integer that things get interesting for us. So let's take a look at what such a series expansion might look like and see how the binomial coefficient might come in handy. So we know in order to do this, if we have f of x is equal to 1 plus x to the p, and we're trying to build this at, let's say, a center of 0, then f of 0 is just 1. When we take our first derivative, we're going to get p times 1 plus x to the p minus 1. And f of 0 is then going to be p. F double prime of x is going to be p times p minus 1 times 1 plus x to the p minus 2. And f of 0 is now going to be p times p minus 1. F to the third is p times p minus 1 times p minus 2 times 1 plus x to the third. And f of 0 is p times p minus 1 times p minus 2. So you can start to see the pattern here. And so we can see that for the nth derivative, we're going to get p times p minus 1 times p minus 2 all the way down to p minus n plus 1 times 1 plus x to the n. And the nth derivative at 0 is going to be p times p minus 1 times p minus 2 all the way down to p minus n plus 1, which means that when we put this into our Taylor polynomial, or our Maclaurin series, we get the sum from n equals 0 to infinity. We get f to the n of 0 over n factorial times x to the n. But notice that f to the n of 0 over n factorial is going to be p times p minus 1 times p minus 2 all the way down to p minus n plus 1 all over n factorial, which is the very definition of p choose n. So we can see that our Taylor series or Maclaurin series expansion of 1 plus x raised to the p power, where p is not an integer because we don't need an infinite series expansion for this when it is an integer. This is just going to be the sum from n equals 0 to infinity of p choose n times x to the n. So our last task is to figure out where this converges. And so we can see that we're going to evaluate the limit as n goes to infinity of the absolute value of p choose n plus 1 times x to the n plus 1 over p choose n times x to the n. So we need to figure out what this ratio is, p choose n plus 1 over p choose n. So let's examine that. P choose n plus 1 is going to be, we'll have an n plus 1 factorial in the denominator. And then our numerator looks like p times p minus 1 all the way down to p minus n plus 1 plus 1, which becomes p times p minus 1 all the way down to p minus n. And that's still over n plus 1 factorial. P choose n, however, is p minus 1 all the way down to p minus n plus 1 over n factorial. If we flip that second one over, we get that this is p minus 1 all the way out to p minus n over n plus 1 factorial times n factorial over p times p minus 1 all the way out to p minus n plus 1. Well, each of the terms in this cancels with a corresponding term over here. And of course, n factorial and n plus 1 factorial give us a lot of cancellation. So what we end up with is p minus n over n plus 1. So if we take that and we put it back in this limit up here, we get the limit as n goes to infinity of the absolute value of p minus n over n plus 1 times x. Well, this limit is 1. So we get the absolute value of x. And our goal here, again, was to find the interval of convergence. So we can see that our interval is, at a minimum, it's going to be -1 to 1. And it turns out that the endpoints change depending on what your p-value is. So you can examine those on a case-by-case basis. All right, let's put our formula to work in order to estimate the cube root of 1.14. So we're going to let f of x be equal to 1 plus x to the 1/3. We know that that is equal to the sum from n equals 0 to infinity of 1/3, choose n, times x to the n. We want the first 3 terms of this. So in other words, we want when n is 0, when n is 1, and when n is 2. And we're evaluating this when x is 0.14 because we have 1 plus x and we're evaluating f of x equals the cube root of 1.14. So when n equals 0, we have 1/3 choose 0 times x to the 0. Well, 1/3 choose 0. The definition of that is just 1. So our first term is 1. And then we're going to add to that 1/3 choose 1 times x to the first. Well, 1/3 choose 1 is just 1/3. Our next term is going to be 1/3 choose 2 times x squared. Well, that's going to be 1/3 times 1/3 minus 1 over 2 factorial, which is just 2, times x squared. So we're going to say f of x, or f of x is approximately that if we're just using 3 terms, and that's just 1 plus 1/3 x. And if we clean up this last guy, 1/3 minus 1, that's -2/3. So we end up with minus 1/9 when we simplify with the 2 factorial on the bottom, x squared. So that f of 0.14 is going to be 1 plus 0.14 over 3 minus 0.14 squared over 9. And that is going to give us approximately 1.0445. Okay, in our final example here, we'll get a little more practice creating new series from old ones. So we want to create a series, the Maclaurin series, for the function f of x equals the square root of 1 plus x squared, which is of course the same thing as 1 plus x squared to the 1/2. So it looks a lot like something we could use our binomial series for. We know that 1 plus x to the 1/2 is going to be the sum from n equals 0 to infinity of 1/2 choose n times x to the n. And the big difference here is that we're replacing x with x squared. So we know that we could do the same thing within the series formula. So f of x then, 1 plus x squared to the 1/2, must be the sum from n equals 0 to infinity of 1/2 choose n times x squared to the n, which is of course x to the 2n. Now let's go ahead and find a radius of convergence for this. So we're going to look at the limit as n goes to infinity of the absolute value of 1/2 choose n plus 1 times x to the 2 times n plus 1 all over 1/2 choose n times x to the 2n. We saw before that this piece right here, 1/2 choose n plus 1 divided by 1/2 choose n, is going to be equal to 1/2 minus n over n plus 1. And then we have times x squared. And we can see that this part of the limit, so this is going to be actually the absolute value of x squared times the limit as n goes to infinity of the absolute value of 1/2 minus n over n plus 1, which is 1. So we get the absolute value of x squared, which is less than 1. And so we know that our interval is -1 to 1. And it turns out that this one actually converges at the endpoints. It's more work than we're going to show here, but it is true. So our interval is actually the closed interval from -1 to 1. So wrapping it all up, we know that if we define the binomial coefficient p choose k as p times p minus 1 times p minus 2 all the way down to p minus k plus 1 divided by k factorial, then the Maclaurin series for the function 1 plus x to the p, where p is any real number, is going to be the sum from k equals 0 to infinity of p choose k times x to the k. And we'll bear in mind that we don't need to use this when p is an integer because, of course, we can just expand that out by hand. This is most useful to us when p is a fraction. It enables us to estimate the roots of various numbers fairly easily.